Well, we're going to do something a little different today. I thought we'd initiate our new cooking series, and today we're going to discuss how to make a peanut butter and jelly sandwich. Why are we going to discuss this? Well, to make a peanut butter and jelly sandwich, you got to have peanut butter and you got to have jelly. You have to have both. When you're setting up your wireless microphone system or in-ears, you have to have two things. You have to have both of them. You have to have a clean RF signal, radio, uh, electromagnetic wave radio signal getting from your transmitter to your receiver. And you have to have a clear channel to tune it to when you do that. You have to have both things together, right? Just like a peanut butter and jelly sandwich. You could have a jelly sandwich, you could have a peanut butter sandwich, but it ain't peanut butter and jelly unless you have them both. Okay, enough of the excitement. So, what we eventually are going to be talking about today, keep this in the back of your mind because we're going to take a little bird walk to get there, but this is our new spectrum recorder. And this is the simplest, easiest way to get a super high quality scan so that you can do frequency coordination. So that we can find that clear channel to tune to, right? You've already got all your RF venue antennas and distros and cables and all that stuff. We got the radio signal. That's one half, but we have to put it on a clear frequency that's invisible. So you got to be able to measure it. And this new tool makes that very easy and very fast. Okay. So we all know that we have to get a signal from our transmitter, through the air into the antenna, down the chain into the receiver. And when it gets there, we have to have a high enough dynamic range that makes that wireless successful. That's about 20 dB, right? So obviously more is better, but this is what has to happen. And so what that means is the signal has to be 20 dB stronger than whatever the noise floor is. So let's talk about the noise floor. So we have this RF noise floor. Right now you are sitting wherever you are, unless you're in a cave, 50 miles under the surface of the planet. You're being bathed in RF radio waves. They're coming at you from everywhere. They're being caused by all these things. Obviously, any kind of a radio transmission, be it radio, TV, CB, Wi-Fi, cell phone. We're getting junk from computers, computer chips. We're getting more noise and junk from video screens, LED lighting, that kind of thing. We get junk from electric motors. We get environmental junk from weather and lightning and cosmic junk from outer space. All right, so all that stuff adds together and makes this little tiny bit, hopefully little tiny bit of RF energy right where you're sitting right now. That noise is already there. And there's really not a whole lot we can do about that. We can try to shield to block it, but I mean, it's basically there. You're not going to turn off every television station in the world. You're not going to shut down cell phones. These other things have to work. So all these things have to work, and it creates a little bit of noise. There's a second half to this noise, and there's the RF noise that we create when we turn on transmitters. And it's called intermodulation distortion. Okay, so that's a noise that it isn't there until you start turning on your radios in the room. And then you create this additional kind of noise that kind of looks like this, right? So I got my 4 microphones there in the middle, and they're generating all those other spikes. That's intermodulation distortion. That's the noise that we create and add to the existing noise floor. All right. So it's a pretty straightforward thing. This is basically just caused because our radios aren't perfect. They're nonlinear, and this is simply harmonic distortion, just like you know it from audio, except it happens a lot worse typically with radios than it does with audio stuff. It's easier to do at lower frequencies, harder to do as the frequencies get higher. So it's very predictable what happens. We tune our two microphones to a couple of frequencies, and when we do that, they generate a sum frequency sideband and a difference frequency sideband. Okay, so it's very well known what's going to happen. If I have two mics and they're tuned to 590 and 595, these are the first principal of strongest harmonics. Actually, there's a whole bunch of them, but these are the strong ones. Okay, when I add another mic, I'm not adding 1 to 3, I'm adding 1 to 4. So this builds up factorially, right? Which means 3 times 2 times 1. By the time we get to 8 microphones, or 4 ears and 4 mics, 8 radios, right? The number of sidebands created is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,000. We know 40,000 frequencies that are gonna be there. Now, most of them will be super low in power, but we know exactly what frequencies they're gonna pop up on, depending on what channels specifically we tune our microphones to, right? So we get to define where this intermod is gonna be, right? So when we do a frequency coordination and we select the frequencies for those mics, that sets the frequencies that these other intermodulation sidebands are going to be at. This is greatly simplified. Obviously, I couldn't put 40,000 of them on there. Okay, so what this means is you can't tune to any of those other frequencies. And depending on where you're standing on your stage in relationship to your next wireless microphone, these are going to come up and down in level, right? So if you're far apart from all the rest of your transmitters, these are going to be low. If you get together and hug somebody and sing together, all of a sudden those particular frequencies are going to get really high. Some other ones are going to get low. And if you have another wireless microphone channel that's tuned close enough to one of those frequencies, when you got 2 people or 6 people, with a gang hug singing together, you're going to knock those other channels off the air, right? So your system's all set up, it's mostly working, and every once in a while you get a little dropout. Most of the time I see this, I have to say it's because the frequency coordination isn't as good as it could be. Now, if you can guess and make it work, you can. You're lucky. On top of a mountain in Idaho, that's not nearly as difficult as it is in the middle of Times Square. So wherever you are is going to determine how much this is going to interact with you. But the best practice is to know where all these spikes are, tune your mics appropriately so these spikes don't screw up your mics, right? That's what we have to do. That's the second half of this, right? We got the signal there with the antennas and the distros and the cable. We got to tune them to these spots. We have to have both things or we don't have our peanut butter and jelly sandwich, right? Okay, so how do we do that? We use a frequency coordination program. This is RF Venue's Wireless System Builder. It's a free app on our website. You just go to it. You don't have to download anything. You don't have to register for anything. It's very simple to use. You put the name and address you put the address of your venue. On the next page, you tell it what mics and ears you're using, and then it spits out a coordination based on what the FCC is telling us about that location within the last 24 hours. So if you're looking at this, basically those red bars are over-the-air television, broadcast television. And you're not going to compete well with those 500 kilowatt transmitters with your little 10, 20, 30 milliwatt wireless microphone. So you got to avoid them. So you can see those black strips. And so this coordination that it would give you is setting those frequencies so that those frequencies aren't bothered very much at all by the intermodulation that those frequencies are going to create, right? This is pretty good. But what this can't know about local conditions inside your venue, right? So if you've got some things inside there, um, so I mean, certainly you've got some computers, you probably got some LED lighting. You know, if you've got an X-ray machine on your stage, not that I've ever seen that, but if you've got something big that is creating interference, um, this program can't know that without a measurement. So this is its best guess, assuming that you don't have horrible things, but you might, you know. So what you need to do is take a scan, measure what's out there in your space, in your venue, okay? And you click on this button and you upload your scan. You just drop it right onto that little box. And when you do that, um, well, these are some scans you can get from the Spectrum recorder. This is maybe this should be a little farther down. Well, anyway, what happens is when you import those scans in, now it can see. Now, if you look at there's a noise line at the bottom, and you can see where these television stations are, how much power is in them. And, you know, now it knows what's there and what's not there at the time you did that scan, which should be reasonably close. And so you can see it's moved those frequencies a little bit. You see the little skinny orange lines, these little lines in here. I don't know if my cursor shows when you're seeing that, but those are the frequencies. And this, if we looked at the whole page, it would list exactly what frequencies those are and tell you which mics to put on what frequencies, right? So that's pretty good. But you have to have a scan, and you have to have a good scan. And that's where Spectrum Recorder comes in. So if you have newer wireless microphones, almost any of the newer ones that will network, you can use the receiver to scan, to measure what's going on in your space. However, it can only measure the frequencies it can tune to. So whatever, if it's in the G50 band or the A1 band or whatever it is, that's the only place it can look. And so when it creates that scan, everything outside that it thinks is zero. It's never zero. It could be horribly full of stuff, moderately full of stuff, but there's definitely stuff there. And you're not going to put that in the frequency coordination program. So the frequency coordination program is not going to make its best calculations because it doesn't have enough data. So when you use this box, it's going to measure everything. So this is what you got to do to use this box. This is, take it out of the package. You literally plug in the power supply. You snap on the antenna. And then I sped this up, but you actually wait 10 minutes and then you stick that thumb drive in there. And when you do, it will have already performed a scan. It scans from 400 megahertz all the way to 700 megahertz. So it's scanning much wider than you could tune your wireless microphones. I'm assuming I'm speaking to people in North America right now. But even in the rest of the world, that covers most everything anybody could use. So when you stick the thumb drive in, it automatically transfers the data. When you plug the power supply in, it starts scanning immediately. And every 10 minutes, it writes that scan to a file. And then it moves to the next file and the next file every 10 minutes, and it'll do that for 90 or 99 days. It'll do it for so long, so much data. Yeah, you might have to deal with that. It also averages this. You can get peak holds and all that kind of stuff. So you now have that data. And then all you have to do is take that thumb drive and stick it into your computer, and then drop that file right into our program or Wireless Workbench or SoundBridge or Spectrum Manager from Sennheiser, Audio Technica, IAS. They all use the same .csv files, okay? Now, if you have an existing system, the best thing to do is to use the antenna that you're going to be using to capture the signal that you send to your receivers, right? I'm assuming wireless microphones. Ears would be the same thing, but backwards. Okay. So, because when you're using a directional antenna, like this diversity fin, it's only picking up signal in one direction. It's basically picking up a third of the pie, and it's basically ignoring the other 2/3 of the pie. Well, whatever garbage is in those other 2/3 of the pie, it really never gets to the receiver. So I don't have to worry about that information. I only have to worry about the information that's actually going to get into my receiver. Now, if this is a new installation that you're doing, and you don't have a system in there, then using the little whip antenna is going to measure everything in 360 degrees so that you're capturing a picture of the entire room. Because you have to start somewhere, and so that's what you're going to do. One question that I get asked a lot about scanning, so you're going to have an A and a B antenna. Do I have to use both? The answer is it's probably better. You should do this twice, but the difference is probably so tiny that I almost never do it. It could be, but it's likely that both antennas are pretty much going to pick up the same thing as far as noise in your room, right? We sort of accept that the noise is basically the same everywhere in the room. It's not, but remember, this is thousands of things averaging out. So that it's pretty much the same. It's just like, the temperature in your living room. Well, you could move over 2 feet on the couch and it's technically different, but it's not really. And it's kind of the same thing with noise. So we're just gonna, for general purposes, if this is NASA, they'd do something different. But for our purposes, the difference is probably so tiny that it's unlikely that it's going to ever be a problem to you. So, but if you have an existing system, I show it here tapped off the distro. You could just connect the antenna directly into the Spectrum recorder as well. That really doesn't matter. Either way, that antenna is getting into the Spectrum recorder. So whatever's the easiest thing, right? Now, you also can set this up on a LAN network. This takes a little bit more work. You have to have a switch, and you have to have some software in your computer. But doing this allows you to set that Spectrum recorder in a place, and then you're able to monitor it from your computer anywhere in the world. So if you're installing a new system for a customer and they're 600 miles away from your shop, you could set this up for them. You can then watch from your desk everything that's happening, should you want to do that. Or you can just have them copy the data off that thumb drive and email it to you, or mail you the thumb drive. And then you've got all that information that you can put into the program and get a very good frequency coordination. I should say that this device, so this is not a real-time analyzer, okay? You're always going to be somewhere about 10 minutes behind the real time. It's pretty close to real time, but it's not real time, right? So you're going to be 10 minutes late. So, if you can live with that for it, in terms of frequency coordination, that's fine. Now, if you want to do some other things, if you're trying to track down specific RF interference or something, we have another product, the RF Explorer Pro, which is a wonderful device. But this This device makes a super high quality scan. It is scanning 12,000 data points between 400 and 700 megahertz. That's a lot. That's see the more data points you have, the better quality your scan is, the better um, the better that your frequency coordination program can calculate out a frequency chart for you, right? So you want super high data. You know what? Just so you know, I mean the old RF Explorer, the little handheld silver and white ones, you know, they did 112 data points. This does 12,000. There's very fine tooth comb that we're sorting all this stuff through. In fact, um, that's more than twice the only other device that I know like this. Shure makes something called a spectrum manager, which sort of does what this does, but I believe it does about 5,000 or 5,500 data points. This does more than double. Now that's a cool device if everything's networked, but that's a $5,000 device or 5,500 bucks, and this one's $799. So if you need all the stuff that other one does and you have a big network system, that might be a choice for you. But for everybody else, the price of this and the super high quality of this system just can't be matched. So when you get better data to give a frequency coordination program, ours or anybody else's, by the way, all these programs use the same math to calculate what they're going to do. It's a very straightforward calculation to figure out every one of those intermodulation frequencies. It's just plain math. It's not very difficult at all. So we're all using the same thing. The difference between all these programs is the user interface, what you got to do to set them up. Now, in the case of our wireless spectrum builder here, it does have a limit of 25 devices. So if you're trying to use 50 devices, you're going to have to use a different program. But if you were only using 25 or fewer, you'd get the same answer if you set it up the same way. This program is really good because for 98% or 99% of people using wireless microphones, this is set up to do what they need to do without having to switch any buttons, turn on any filters, assign any frequency block, all that kind of stuff that you can do in the others, which is really good if you know how to do all that stuff. But if you're not quite sure what some of those numbers mean and you screw it up and you don't set your program up properly, then you're going to get a result that may not be the best thing because you didn't set it up right. So this one is pretty hard not to be correct for almost anything of what I would consider normal. Obviously, there's screwy stuff that people can do, but for everything that I would consider normal, this just out of the box just works. Just plug in stuff. So when you have a real scan and better data, you get a better coordination. Do you need it every time? I don't know. Depends where you are. That's why you're getting little dropouts on your stage. Now and again, your system's working great, and 2 or 3 times in an hour, you get little noise or the mic cuts out for half a second or something. There's a very good chance that the frequency coordination has contributed to that. So, Spectrum Recorder, $799. It's so easy your mother can run it. That's the great thing about this. You can buy all kinds of tools, but if you can't run them, you know, our RF Explorer Pro is a wonderful device, but it has a pretty steep learning curve. You're not going to take it out of the box and become an expert. You're going to have to put in some hours and hours and hours. Now, it'll do a whole lot of things this won't do in addition. But if what you need to do is a frequency coordination, this is plug and play. I mean, just plug all the stuff in and you're pretty well there. So this makes super high quality scans at a reasonable price and you can't screw it up. So there's your peanut butter and jelly sandwich. It's just done. Looks good. Actually, it's about lunchtime, isn't it?
You're making me hungry, Don.
There you go. Man, isn't it a really good peanut butter and jelly sandwich is really good too. Okay. So with that, that is sort of my presentation. Um, we got some questions, Adam?
Absolutely. We got some great pre-submitted questions, and don't forget you can throw those questions in the questions and answers tab. Myself and Richard will help to answer those, and certainly we'll call them out for Dawn as well. So let's go with the first one. Will wireless workbench see this device in the network, and can it be used to scan in real time?
Uh, so no. Um, None of the programs that I know of, I don't think any of them, will run directly. What happens is this creates a data file that you have to load into that program. I don't know of anything that's automatic that'll automatically do that. Maybe someday folks will do that, but I think it's a USB thing that sort of limits that from happening. So no, it you can't automate it. Again, it's not in real time. It's within the last 10 minutes, kind of depending on where you are in time. Just consider your scan to be 10 minutes old, so it's not in real time. But the fact that when you go back and look at that list that we looked at, that has a scan for every 10 minutes, right? So if you find out on Monday that your church had a problem between 10:40 and 10:50 a.m., you can go back and find that file. They're cataloged in every 10 minutes, and you can pull that particular one up. You would be able to see probably a spike that was a particular interferer that time.
Awesome. I think clearly getting the fastest way here is on the network where you can just open the file and load it into Wireless Workbench and you're moving on. So that's definitely the easiest. So next question. Can it analyze analog and digital wireless systems at the same time?
So the answer to that is yes, because remember, what it's analyzing is radio waves, right? And radio waves are all analog. Analog and digital, when we're talking about wireless microphones, we're talking about their modulation schemes, right? So we all know AM and FM radio. Now we can include digital radio. It's a modulation scheme, but the radio signal, the invisible electromagnetic wave that's flying through the air, is analog, regardless of the modulation. So no problem. Yes, you can mix systems, no problem at all. You're good to go.
Awesome. All right. When coordinating IEMs, at what stage does the pack gain level affect the noise floor of the signal?
Well, we're talking about, I think we're mixing two things here. So there's an RF noise floor and there's an audio noise floor. So the gain, how strong, how much audio you're running into your transmitters, where you have the gain set on your transmitters, um, that's your signal to noise ratio in the audio world. But in the radio world, the gain, well, it's not zero, but it's so minimal. I would consider that it doesn't make any difference to the RF signal. I mean, I suppose there's a way that could happen, but in the real world, it would be a tiny fraction because basically the radio wave doesn't care. So so setting the gain in the audio world is something that you need to do to keep the hiss down in your in-ear monitors. You need to set the gain as strong as you can without clipping. That raises it as far above the noise floor as you can get, right? So if you're using, so that's one of the reasons that people like the Sennheiser G3, G4 in-ear monitors, because they don't have a companding circuit, right? So the companding circuit that other companies use to keep the hiss down affects the audio quality, right? It's like running it through an old DBX noise reduction system. Some people that bothers, some people don't hear it, but it alters the audio quality. So those systems tend to be hissy if you don't get the gain set really good. Not much of a problem for a rock and roll band. And if you have a quiet, spoken word only church, you're going to hear hiss like crazy. So although you probably don't use intermonitors in that case. But anyway, so there's an audio noise floor and there's a radio noise floor. The radio noise floor is what we're concerned with in locking in the signal and making it work. The audio, so we don't want any dropouts, but your audio signal might be noisy. That's two different things.
Hey
Awesome.
Don, could I add to that too?
Sure.
Okay, so sometimes some gear will let you attenuate the received signal coming in overall. So if you do have a noise floor you just want to lower, you can lower the whole noise floor and picture that as you're reducing everything coming in, and you make sure carrier pop out a little more. Even if you're on a clean TV channel, you may want to lower the noise floor. For some reason, your environment may be causing you things. There's a balance between lower noise floor setting and the carrier coming in, and sometimes you can have manual control of that. And then on, for example, in-ears, yes, you can adjust the squelch setting. So if the squelch is adjusted, it'll affect the RF noise coming in, and that could change a range. A lot of times on in-ears, I would lower the squelch, meaning open it up to get more range if I know I'm on a clean channel. So
Yeah.
those are just different angles of fine tuning things is on the RF side of the noise level. So, it does affect your audio noise floor too. They're all kind of related, let's say.
Yeah, you've got a 10-pound bag of stuff. You can have it long and thin, short and tall, big and round, but you've always got 10 pounds, and we're always trying to trade off things
Yeah.
that we don't need. I'll give this away. This is what I need, and I'm willing to give this up. Now,
Yeah.
there's no free lunch. You're always giving up something to gain something. It's just better when you have the choices to do that yourself.
Yep.
But yeah.
All right, great. We got two more here. I would like to know more about the way modulation works on a stereo channel like PSM 1000.
So that's just multiplexed, just like the FM stereo that you've been listening to in your car. It comes in on a single channel, but it has a left and right channel combined, and the way they're coded or phased aligned, the other circuitry can pull that apart and separate that into two bands. So that's really how that operates. So it sometimes feels confusing that, well, wait a minute, how can I get left and right, but it's on a single channel? And it's just the way, again, it's the way your home stereo is with regard to radio FM. That is single, or it's the same way with your TV. Now, if you look at a digital TV station, so you may be able to see on your screen, you go to channel 24 and you have channel 24.1.2.3.4. Or maybe more numbers. It's broadcasting four different programs or six different programs, but it's all on that same frequency. So that's called multiplexing, and yeah, it's been around for a long time. So don't let that fool you. You don't have to have two different frequencies to create stereo.
Awesome. All right, the final question here. Distributor and combiner in a single device, will they have them in the future?
Well, you actually depends how many channels you need. You could do that now with a distro 5 HDR and a combined 6 HDR. So you got one rack space that would give you 5 microphones and 6 ears in a single rack space. I mean, the fact that it's not one box but two that you've bolted together, so that can be done. Um, my best guess is it's probably not done frequently because it's too limiting to the numbers of channels. Um, if we're all using 4 and 4 or 8 and 8 or 16 and 6, whatever it was, but everybody's kind of doing it differently. So that kind of somewhat paints you into a corner. But if you look on our website, our new distro 5 HDR and our new combined 6 HDR are each half rack modules. So in one rack space, you have both mics and ears together. And they're super high quality too. So take a look at that.
Awesome. Well, that does it about that for questions. And thank you for submitting all the questions live. I saw Richard was answering some, I answered some. So we really appreciate your participation in submitting these awesome questions. Thank you, Dawn, for another awesome presentation. We're going to go ahead and post this webinar on our webinars page so you have access to it later. Share with your friends and subscribe to our YouTube page for more. So we appreciate your time. And again, we'll see you on the next one. Take care.
I'm going to go make a sandwich.
Yeah, I'm hungry. Have a good one, guys.
Thanks, guys.